All right. So welcome everyone to another Bluecoat talk. My name's Tyler. I'm one of the small army of Bluecoats at Science North, and I'm here with Dr. Pierre Gorel at SNOLAB, and we are going to be talking about the SNOLAB institution and some of the work that's done there. So first of all, welcome. Thank you for joining us, Doctor.
Oh my, I feel so old when somebody is calling me doctor.
Yeah, okay, thanks, Pierre. Thanks for coming.
Thank you for having me.
Very good. So to start off with, that's a really interesting background going on behind you. Are you underground right now?
Unfortunately, no. I was planning to be, and I was supposed to have some job to do today on the ground in the lab, but some other job was more important, and due to the pandemic measure, basically my job has been bumped. I would be on Thursday on the ground. So right now I'm just giving the illusion. Well, actually, technically, I am on the ground. I am in the basement of my house, but.
So you could have told us yes and been perfectly truthful. We never would have known otherwise. But that
the way I'm dressed would be a dead giveaway, but it will be visible at the end of the talk.
Okay, so that's one thing we can start with. So you wouldn't be wearing an ordinary shirts down underground in the SNOLAB then?
No, I won't. So I would be wearing a special clean lab gear, so some fabric that is not leaving any dust. I would also wear a hairnet, despite my well, not that many hair to keep. And depending on where I would be in the lab, so if I was not sitting at the table and in front of a computer, I would be also wearing safety glasses and a hard hat, as well as safety shoes. And
so you mentioned clean room. So the lab is a clean room, and I already gave away the secret that it's underground. But maybe for those viewers who aren't necessarily familiar with the SNOLAB, you could just give us a very brief idea of what exactly this place is and where it is.
Yes, I will certainly try that. So let me share a few things. So SNOLAB is in Greater Sudbury, Ontario, for people who are from outside of the province. It is in the depth of Creighton Mine, so on the west side, Creighton Mine being one of the deepest mine in Canada. And it is, in fact, 2 kilometers below the surface. Creighton Mine continues a bit further than on this drawing. And what the main thing about SNOLAB is that it is a full facility dedicated for astroparticle physics and low background experiments. So we are in an active mine, and yet we have a full facility, which is a clean lab, meaning level of dust, which are about 1,000 times less than what you would get on surface.
So the dust is important for your experiments then?
Well, of the lack of, meaning, so I guess I should take a step back. So we are looking for particles like neutrinos, dark matter, that are very elusive. So they will pass through matter, they will pass through you. Trillions of neutrinos are passing through you every second, and they don't actually notice, it just passes. And in fact, you can even consider that they don't even pay attention that Earth was on their path. For most of them, they would just go through and continue their travel. So what you do to detect them, you build a very sensitive detector, usually fairly big, and you are trying to look for that interaction, that signature that a particle actually went through, left a bit of energy behind, and then maybe continue its travel. And what you get is a situation where, let's imagine you are a scientist in the field. You are trying to listen to a butterfly flying, for instance, and you happen to be just next to an Air Force base, and they are testing jet engines at the same time. So your microphone, your very sensitive microphone, just cannot do anything because it's completely saturated by the noise that you have around you. So what you try to do is to isolate yourself from the noise around you. So you are going to try to build enclosure around to dampen the sound as and as you build more and more, less sound goes through, and then you finally realize that it doesn't matter how many you have enclosures around you, there are still some noise that manages to go through. It's so loud out there. So, to push this analogy a bit further, what you are going to do is to dig a basement and try to get that out. And eventually, as you get deeper and deeper underground, you really have to hard work sometime. That sound goes away, and that's a bit what we do at SNOLAB. So the equivalent of those screamers, those jet engines that we want to dampen out, is all that those very high energy particles that comes from outer space that we call cosmic rays. They have energies all the way to orders of magnitude what we ever create on Earth, even at LHC. And they interact with the upper atmosphere, and by doing that, they create what we call electromagnetic showers. So they interact, they create new particles that are interacting again and again and again until, well, they disappear eventually, or they reach the floor and we can detect them. But some of those particles called muons are big bullies. They are heavy, they are charged, like they are basically the heavy cousin of the electron. They have a lot of energy, and they need literally kilometers of material to be stopped. So in order to remove those muons, we really need to go deep and deep underground, as deep as we can, and that's the idea of SNOLAB. So I'm going to share again something. Not leave the meeting. So this is what basically we do here at SNOLAB. So we have on surface, we have about, and of course I have a share window just on top of my thing. We have a few hundreds of muons per square meter per second on the surface. And at 2 kilometers underground, we go to less than a muon per square meter per day. So that's the power of being far underground, having all that granite rock on top of us, and the reason why we built a lab here. Of course, the mine was the reason why it is here at Creighton Mine, but that's the opportunity that the mine gives us. And of course, because we don't really like being all the time underground, we also have a surface facility so that we can sometimes see the sun.
Okay, so you've got a facility on surface that lets you see the sun, but there's too many muons, these heavy electron particles and other particles coming from space there, hundreds per second. And you go underground, you're 2 kilometers, and the solid rock is able to block that out. So the muons are the jet engine sound that's keeping you from hearing the signal that you're interested in. That signal is these neutrino particles. Is that right?
That signal is either neutrinos, which is historically what SNOLAB was about, and now SNOLAB is about a lot about dark matter. And dark matter is even more elusive than neutrinos. At least neutrinos, we know how to detect them. Dark matter, so far, we have not been succeeding.
Right. So we've been able to detect neutrinos. There's been excellent work on neutrinos done at SNOLAB in Sudbury, a Nobel Prize awarded a few years ago, in part for that work. And now we're also investigating dark matter, which is, I guess then it would be another sort of very small particle that, like the neutrinos, would be able to get down through the rock. Is that accurate to say?
So that's one of the working hypotheses for dark matter, yes. So what we know about dark matter is actually very little, hence, in fact, the name. So back in the previous century, and all the way from the 30s to the 70s, astronomers have been seeing some funny things by looking at galaxies and clusters. So what holds the galaxies together is gravity. So the mass of the stars that are at the centers are holding the stars that are further away, and so on and so forth. And the galaxies are turning, and clusters of galaxies are also spinning around, and the speed at which they can spin for a given radius is basically given by the mass contained within the sphere of that radius. I don't know if I... So basically, if you don't have enough mass, a star that will be at a given radius, if you don't have enough mass to hold it there, the star will just go away. So, and by counting the number of stars, or if you are looking at clusters of galaxies, the number of galaxies, you can evaluate how much mass you contain, how much, and all that mass, how much gravity it generates, and if it's consistent with the speed at which that star or the galaxy is going.
Okay.
And
so
what
the stars are bright and glowy.
Yeah.
So you can see them and count them, and so then things are moving faster. So there's not. So the stars, you count them and you say, okay, there's not enough stars for the gravity we see that's holding things together. So there's something that you don't see. So then it must be something dark. So that's where the dark matter comes from, right? That's why we call it dark.
That's correct. That's the initial idea. Nothing is producing light, so it's dark. But it goes further than that. It's so if you instead of looking at stars, you actually as stars themselves, you consider the stars as a background. So you consider the light that comes from the stars. You can actually infer some heavy elements in between that will not produce light or not absorb light even, just by the fact that because of that gravity well produced by that heavy element, the light goes around and changes direction. So if you happen to be just in the axis of the star, the gravity well, and yourself, then the star is suddenly going to look bigger. But if you are in a, oops, I'm going too far.
Maybe you could stop sharing your screen for the moment.
Yep.
You're not using your graphics. We can see your lovely face. And more importantly, my lovely face. Okay, so let's get back to the topic at hand. So gravity is actually able to bend light like a lens. And looking at this bending, you're saying we can tell that there's something in the way. Oh, wonderful. You do have something for that.
I do have something for that. You at Science North has also something like that. If I recall, you have what is that? A black hole simulator or something like that.
Yes, we have a lovely gravity well. You can throw your marbles through and see how they're bent in their paths by the curving of space from that gravity. But it works not just for marbles, but for light as well.
So the big difference with your gravity well is that your gravity well first has a hole at the bottom, and second, you cannot send your marble fast enough that they actually well, sorry, I rephrase that. Kids do that very well. Send the marble so fast that the marble goes away the other side. But kids and less kids. Anyway, the idea is the same. You are going to see this distortion of the light, and you are going to see due to the gravity well. So if you are in the correct axis, you see a bigger, which is why it has been called gravitational lensing. However, the picture is not exactly true, because if the gravity well is not spherical, for instance, you actually can see multiple times the same element, just because, well, the way the light is distorted. Or you can also see some interesting fringes in the sky. So that's not in the case where you are not exactly in the axis, but actually slightly off. So you are going to see a fringe like that, and smiley face in the sky.
Okay, so this image you're showing us, the bottom one, there's two yellow sort of eyes, and those would be foreground galaxies, and then the blue smiling part that's what's being lensed. Is that right?
So you probably have a dark heavy stuff somewhere in the middle here,
Yeah.
and so you see the two which are probably exactly the same object, and then those fringes on the sides are indeed galaxies that are reaching the edge of that light. What is that? Distortion, and then you have you see only a fringe, not a full object.
It's certainly very happy looking, anyway.
I'm sure somebody was when seeing that picture.
That would have made your whole day, I'm sure, especially if that's what you're researching. But for what you're researching, what's important here is that this mass is not visible. And so it's this dark matter. It's transparent. The light's going through it. And so we know that there's something there that can't be seen. And so this is where we get back to this idea of dark matter as being an invisible substance in the universe. Is that where we're going with this?
Yes. So that's really the only thing we are sure about dark matter. We know there is something around us, within all the galaxy pretty much, and between galaxies, within clusters, there is something that does not shine, does not absorb light, does not change the colors or anything like that. Just light, obviously, is totally, that matter is totally transparent to light, or to other particles for that matter. We don't see any high energies particles coming from those regions. And yet we see that there is gravity, so there is a mass. And one of the main candidates for that dark matter is something that we have been dubbed as weakly interacting massive particle, so WIMPS. It used to be a play between the machos and the WIMPS. So the machos were interstellar objects, so black holes and big but not brightly shiny stars or things like that. And the machos eventually were pretty much ruled out. There's still a bit of contribution here, but the WIMPS stayed.
That's very apropos for the modern world. The machos just can't hold a candle against the WIMPS. So there's not nearly as many machos, these massive halo objects. These that would be, oh wow, you're sorry. So
Very funny.
These would be things like black holes or objects that aren't giving off light in outer space that you could say, okay, they aren't giving off light, maybe they're some of this mass, but we looked for them and they aren't there. So
well,
that
not nearly enough.
Not enough of them. Okay, so that means at least most of the dark matter, if not all of the dark matter, is going to be these WIMPs, which I love the name, the weakly interacting massive particles, or some other kind of particle, because of course, WIMPs are just number one on the particle list.
Yes. So the WIMPs, the idea of the WIMPs is that they are, so they have a mass. They don't interact electromagnetically, so they have no interaction with light. They would be cold, meaning they would be able, when we mean by cold, not relativistic, so they would actually make, being able to not agglomerate, but make structures. If they had too much energy, if they were going too fast, they would just be a diffuse background, and instead we see that they're actually making structures due to their gravitational interactions. And we would be within the Milky Way, and we inside a halo of WIMPs. So Earth, as it travels, following the solar system, travels through the Milky Way, would just be all the time suggested to a WIMP wind. And those WIMPs will just pass, well, actually, will pass through us, or we pass through them depending of a referential. And so the idea that we have at SNOLAB and over labs of the same kind would be to build detectors, and those detectors will be a bit like big nets trying to catch a signal of those WIMPs as they go through.
Okay, so to use a very Northern Ontario analogy, the Earth is, say, your canoe, and we're paddling along through a giant cloud of mosquitoes, except these mosquitoes are not stopping to bite us.
Okay, I bite. Of course, I'm not going outside those days for some reason, but
I know, I'm in withdrawal. I'm trying to bring a nice picture of it. So we've got a cloud, and we're passing through the cloud, and the clouds, the particles in the cloud are passing through the Earth as we swim through this cloud or travel through this cloud. And some of these particles will hopefully, knock on wood, be stopped in our detectors. Now, we don't know what these WIMPs are, so how do we catch them? How do we know how we can slow them or stop them or detect them if we don't actually know what the particle is?
So that's the thing about WIMPs. So the part about weakly interacting means that we would know how they interact with matter. Of course, it's a working hypothesis, but if those WIMPs exist and they indeed pass through, they should knock on nuclei of atoms from time to time. So if enough of those are passing through and you have a big enough detector, then you would see a signal which will be basically a snooker ball. So you will see the nuclei moving away and leaving a signal in your detector. Okay, and that's the signal we're looking for.
Okay, so we're not actually detecting exactly these particles. What we're detecting is the movement of the atoms, of the nuclei of the atoms, say, that have been struck. So it's been hit by this particle, bang on. I suppose it has to be a very direct hit, and then it's just pushed us a little bit, and then that little bit of movement is some energy, and then you're going to be able to detect in some way.
In some ways. So what you need to do is to make sure that no other thing in your detector does exactly that. So or that you can recognize that the interaction has been a nuclear recoil, so the nucleus going away, and opposite, for instance, to an electron going away, for instance, a photoelectric effect. And you need to make sure that the energy range, so the amplitude of a signal you're going to see, is consistent with what you expect. So luckily for us, we actually know another particle that is readily available on Earth that makes that same of interaction. Actually, luckily, it's a double-edged sword. Neutrons will do exactly that. So the good thing is that we can use a neutron source and calibrate our detector. So see that our detector is working the way we expect it to be. That neutrons will be detected with that kind of energy, and that this signal will have enough different characteristics than the rest of our loud noise that we get from other places. And of course, the second side on that coin is that because neutrons are doing the same thing, we want neutrons to be out of the detector when we are not calibrated. So I'm back to my analogy of this very sensitive microphone and how you build layers upon layers to isolate the sound. What we do is a bit of that. So I'm going to share a bit more as soon as I get my...
So I imagine neutrons are going to have a fairly hard time getting through 2 kilometers of solid rock between us and the laboratory.
The main problem is that they are already there. So when we are talking in our world, what we are talking about, the equivalent of the noise, the background noise that we had for this very sensitive microphone, is the natural radioactivity. So we have those radioactivity alpha, beta, gamma. So the exact nature of that radioactivity is not really relevant. But what you need to know is that you need to absolutely get that out of your detector, and failing that, you need to be able to recognize that so that you can push that away. So the neutrons are a different beast because they are difficult to stop. Not as bad as muons, but they still are relatively difficult to stop. But they do exactly the same signal as dark matter. So we cannot have them in the detector because then it will just make a false positive. So what we do is we have that layer upon layer of our onion shell policy. So we have neutrons, gammas, betas getting to our detector, and we build layer upon layers of shielding. And each layer is cleaner than the previous one. So the previous one is going to add a bit more of background, additionally to stopping most of what was before. But so as you are going closer and closer to your detector or microphone, you need to be silent, more and more silent. So here, being 2 kilometers underground is a bit of an issue here because the rock around you is radioactive. You have always a bit of radioactive material inside the rock, no matter which one it is. Granite is actually one of the annoying ones. Some labs are in salt mines. Salt is a much better surrounding material.
But there aren't any salt mines this deep.
Not that I'm aware of, especially since salt is flows with time, and being 2 kilometers underground puts quite some stress on the rock. So I'm afraid a salt mine that deep would just collapse quickly. So what we do at SNOLAB is usually have a first layer, which is water. We are very good at having very pure water, and that's cheap to make, relatively easy to build. So we put few meters of water around our detector, and then we have a second layer, which is cutting out, for instance, lead or copper as you're getting closer and closer. Copper can be done, can be made very pure, but is relatively expensive. So you just get purer and purer as you get through. And then eventually what you get inside is your detector itself. And unfortunately for you, your detector is usually slightly radioactive himself. So there are all the stuff you didn't manage to get through, plus the stuff that you actually create in the detector itself. So you have to go through signal treatment and figuring out where the event happened and what characteristic to try to get that away. So in my analogy of a microphone, that would be basically trying to play with the frequencies to isolate the background noise so that you can hear what you want. For instance, cutting down to your own breath in the recording. And of course, there are still the neutrons that we want to get out, and that is usually done by the shielding.
Okay, so the neutrons that are the really bad ones, they're blocked by the water and the plastic, and everything else that has gotten through the rock and the water is hopefully going to be partially, at least mostly blocked by the lead and the copper, but then you still have the material that you're using as your detector, and that is radioactive as well. So basically, is there anything that isn't radioactive on this planet?
No. No.
Okay.
That's not even a short answer. Is basically the only question is how clean do you need it? But no matter what you do, you will get a bit of radiation in your detector. It may be lower than the sensitivity of the detector that you are using to measure, sure, but it will be there. And because we are constantly bombarded by cosmic rays, if you leave something on surface for a while, it is good. Okay, not all of them, because you need to have some reaction happening inside, but some of the materials which will be totally clean at the beginning will start getting activated by the cosmic rays.
Okay, so the radiation coming from space can actually make materials here on Earth become radioactive.
Yep.
Like the carbon-14 that we use for carbon dating.
Exactly. Or well, that's one of the example. Yes. So that you always have a fresh supply of carbon-14 because of a reaction happening in the atmosphere. So now the real question is, how clean do you need, and do you need to be, and can you find a material that is clean enough for your application? And that's all what building a dark matter detector is about.
Excellent. Oh, that's all really fascinating. We do have one question here in the sidebar that's been relayed to me. We've got our wonderful facilitator, Renata, who's been monitoring all the chat. And an interesting question, what is outer space?
That's probably something I should not have said because I'm not quite sure. So I would define it actually for if you are talking about the cosmic rays, and I would define it of actually outside of a solar system and so on. I'm not aware of any source of cosmic rays inside of solar system, but I'm sure the sun itself is emitting stuff that potentially are annoying for all detectors.
So we can take the definition of outer space here. It's the same as the usual definition of outer space, which is everything far enough away from the planet Earth that it's outside of our atmosphere, or up above, far away our heads. That's a fun question, though. Thank you, Anna, for asking that. So the dark matter particles are in outer space, but they're also here on Earth because the Earth is moving through outer space, moving through this cloud of these mysterious particles, and we are trying to find them. Again, just to recap for anyone who didn't catch the first part of this, here in Sudbury, 2 kilometers underground at the SNOLAB. And actually, I'm going to just invite, if there's any other, anyone who wants to throw out a question here, because Pierre and I seem to have just had a nice little pause in our conversation. This would be a good time if anyone wants to toss out any questions. Otherwise,
I'm going to invite you to SNOLAB. So I'm going to actually share again my screen.
Excellent. Yes, that's one I was expecting people would ask. What is it like down there? You know, it's 2 kilometers underground. It's in Creighton Mine, which is an active nickel mine. So you can think, you know, lots of rock, dark, and the occasional drip of water on your forehead. And I suppose that's sort of what we're seeing here would be the mine portion.
So that's the entrance of a mine. If I can actually go to full screen. No, okay, it doesn't work. Never mind then. So here, that's actually the way we are coming to the lab. And this part is the entrance of the lab. So it is still considered dirty, obviously, here. And our first step here is going to clean our boots. Because, so the background, fighting the background is basically the name of the game for neutrinos or dark matter. And being on the ground, putting as much shielding as you want is going to be useless if what you do when you come in is walking on your stuff and dust is falling from you on your detector, stays there, and then what you are measuring is basically what that dust and not anymore anything else.
Right,
so,
because everything's radioactive. The dust in the mine, we all know mines get dusty. That's also somewhat radioactive. So that's going to be something we want to keep out of the lab.
So we're lucky the 6800 level where we are is not active as mine as ore production. So it's not too dusty, but yes, it's for low background detector, anything is dusty.
Now we have another question coming through. They're asking, Catherine asks, is SNOLAB and its experiments affected by seismic activity? You're underground, you're going to get some seismic waves coming through every now and again. There's blasting in the mine, that's going to create some vibrations. Is that something that is noticeable in your experiments, or is that not going to affect your detectors?
The lab itself and the detectors we are building are meant to survive any kind of seismic events that we would expect in here. So Sudbury region is not seismically active, but we have obviously the odd blast and well, actually odd blast is pretty much every day. But sometimes we have that seismic event mine related. And that shakes the ground, that makes a loud noise. And the detectors usually either have some ways to recognize that it was a seismic event. So we have a seismic monitor in the lab, and we have some hydrophones within our detectors to try to cut out the events around that time. But most of the time, it doesn't really matter. They are not really affected by that. It's depending what kind of detector you use. Semiconductor detector, for instance, needs to be fairly isolated from the ground to not get any vibrations, because they are fairly good microphones, amongst other things. Liquid argon detector, so like DEEP I will talk about, or Snow Plus, is not that sensitive.
Okay, so the different kinds of detectors have different sensitivity to the vibrations, but overall we know when the vibration is there because we can measure it and we can just say, okay, that was shaking. We're not going to worry about what we see right at that second. Well, that makes sense. A couple more questions before we go on with the tour, if that's all right, Pierre. Okay, one, a good question from Jen. We're getting closer to the center of the Earth as we go down those 2 kilometers to SNOLAB. Now the Earth is 4,000 some kilometers. So we're not that much closer, but is it getting warmer down there?
Absolutely. Yeah, so it is getting warmer. So the rock is definitely getting warmer. The level that we are, 6,800 level, has been ventilated already for decades. So the temperature in the drift, so the gallery, is about 25 to 28 degrees. It's really depending on the temperature outside. It's warmer in summer than in winter. And if you go deeper, or if you go in drifts that are not as ventilated, you will definitely feel the heat. And I'm told, although I never saw it myself, that in the deepest part of the mine, it is actually fairly hard on people to work there because just of the heat around you.
Yeah, someone can correct me if I'm wrong if they know better, but I heard the figure 40 degrees Celsius at the bottom layer of Creighton, which is, even in the winter, and that's hot. Another question before we move on. Just gonna take one more, and then I would like to see your tour. Marla's asking, and this is the question that I'm sure you've just been dying to hear. Other than explaining super cool secrets of the universe, how are neutrinos useful? Are there any practical applications? I know we love those questions as scientists, right?
The short answer is no. At the moment, there is no applications of dark matter that we would know of. Of neutrinos, actually, they are a bit, but for instance, you can infer the power of a nuclear power plant with neutrinos, by the neutrinos that they are emitted. You can actually, one of the detectors at SNOLAB is trying to detect supernovae using neutrinos, because the supernovae will be emitted before the nova goes off completely. So and because they're traveling at close to the speed of light, they will reach the detector with few minutes in advance. So there is time for warning astronomers that there is going to be a nova. And because there is a network of such detectors around the world, they can tell this is where you are supposed to be looking at to see the nova happening.
Right. Okay. So this supernova early warning network isn't going to tell us we can evacuate the planet. It's just going to tell us, hey, look up in the sky, a star is exploding in a couple minutes.
Where do you want to go anyway?
I don't know. Ask Elon Musk. That's not my department.
And even if you were managing to go on a spaceship, you will not go far by the scale of a nova. It doesn't matter if you are at the one side of the solar system or the other side. You will just be dead. Anyway.
Luckily for us, as far as I know, in my background in astronomy, there are no stars capable of a supernova within a distance from Earth that would actually be dangerous to us at the moment. So we really don't have to worry about that. The early warning is just for astronomers to know so that they can fire up their telescopes and see the event as it happens. So that is an excellent and fascinating practical application of the work you're doing down there.
But if I may actually just say a last thing about that. So about neutrinos and dark matter, well, the applications are a bit difficult to find. But it doesn't mean first that in 50 years or a century, there will not be something that actually be coming out of that. Maybe something absolutely world changing for us. And the second thing is that as we are building stuff and pushing all the time our limits to get more and more cleaner, deeper, more sensitive and so on, we are actually inventing new things which have by themselves some applications in the common world, the real world.
Yeah, the world famous, the spin-off technologies.
Absolutely.
I hear there's a little thing that you, some of you out there may have heard of called the World Wide Web that particle physicists invented to help them collaborate. It's small and just getting started, but it might actually have some applications to your day-to-day life. Look for it somewhere. www, World Wide Web. I tell you, it's the future.
Especially in a case of pandemics and social distancing.
Yeah, especially now.
So let's go on to the tour. Otherwise, we're going to run out of time, and then we'll have to go take the cage up, which is actually a real thing in the lab. You can, if the cage only operates at a particular time. So we don't want dust. So anything that goes in the lab is being cleaned. So we have people dedicated to do that. Here, Brenda was probably cleaning a loudspeaker, it seems to me. Anything from loudspeakers, screws, bolts, cable trays, cables, kilometers of cables have been cleaned to be put in the lab, and so on and so forth. And when I mean everything, I mean also everybody. So the first thing you do after you clean your boots is you get your hard hat and your belt, mining belt on a hook, and then you go to the shower, and everybody goes through the shower, gets out of the clean side. You've got towels, and then you have what I was mentioning before, a clean lab gear. So those blue coveralls, fresh underwears, and so on.
Well, I like the color.
But you like the color?
We're partially blue around here.
We got pretty much rid of the baby blue colors. And then we go to the lunchroom. Oops, there we have a laundry on the ground, obviously, to clean all that. That's a very big job. And we go to the lunchroom where we can wait for the all clear to start working, having a cup of coffee, discussing with our colleagues what we're going to be doing during the day, have our safety talks if we need to, and so on and so forth. So that's our lunchroom is also the refuge. So if something happens in the mine, that's what happens is anything from a fire alarm drill to the cage is down to electric failure, that's where we will be, waiting for the all clear, get back to work, or all clear, we get you out of the lab. And then, well, the rest of the lab. So it's going to be two time consuming to get through that. So I'm going to stop here for a second and show the map.
It is, for those of you who don't know, a very large facility. It's about 3,000 square meters, I believe, of clean room environment, which is over 30,000 square feet. So that's a lot of space to go through.
5,000.
5,000. Okay, well, I said over, and 5 is bigger than 3.
Yeah.
So,
so this is basically what I was showing you here: the lunchroom, the entrance of the lab, and the refuge. So after that, so you have a refuge, lunchroom, showers. That's where we have our toilets too. Flushing toilets is really great in the lab. A luxury that we have. And then, so, say again?
That is a real luxury. For those of you who don't know, generally underground, you're stuck on a porta potty, which is then hauled up to surface. Having a flush toilet underground is quite an accomplishment.
So now the neutrinos detector. So we have, so HALO was this supernova detector I was mentioning earlier. So it's inside that small draft here. SNO Plus takes the full cavity. So for just a bit of background, SNO Plus is what's the refurbished detector that SNO was, so the Nobel Prize winner in 2015. So now the inside of a detector, instead of filled with heavy water, is filled with liquid scintillator. Actually, it's half filled at that moment. They are waiting for the pandemic measure to stop so that they can finish the fill. And eventually we'll look for very special radioactive decay that don't produce any neutrinos. That's what they will have here. And there is a space over there for a similar experiment, but using different materials and more sensitive eventually in that cavern over there.
Okay, so you heard it here, folks. If you've got a science fair project, they have space available.
And you have to be fast because the space in the lab is actually shrinking, a very little space. We do also a bit of biology on the ground. So we have this very specific environment that some biologists at Laurentian are using. So Flames is using fruit flies and looking for the effect of higher air pressure on fruit flies, how they develop and how their metabolism changes. So that's an interesting thing to move fruit flies up and down the shaft several times every day, and then having them exercise in the lab. There's a treadmill in the lab for fruit flies. The repair project is looking for very low background effect on cell development. So we have a fairly good understanding of what's happening to the cells if you have a lot of radioactivity. But as it turns out, very little understanding of what's happening if you have no radioactivity whatsoever. And our working hypothesis for this project is that life actually evolved to use the ambient radioactivity. And if you remove all that, it is actually a bad thing for cell development. And of course, we have a lot of experiments on WIMPS. So some of them are being decommissioned. So Minikin is being decommissioned. Some of them are being built. Some of them here, Deep 3600 and DAMIC are taking data. And PICO is almost ready to restart taking data after a major re-rolling of the detector. So Deep is one of the two experiments I'm working on, and as well as Snow Globe here that is being built.
Okay, well, we're almost out of time. There's a whole lot of really fascinating science going on at SNOLAB. We might have to do this 2 or 3 more times just to talk about all of the different experiments. But we have one more question before we wrap up. And this is a little bit more personal. It's Jen asked, she just was wondering what the most exciting thing that you've discovered with your research, the most exciting thing that you've learned, the thing that made you stand up and shout and call home. And
oh, geez.
They don't have easy questions for us today.
No, they don't. Well, I didn't make any major discovery, so unfortunately that is off the list. But probably the most disturbing, the most exciting things would be trying to figure why events are coming in a very specific way and not in a what is that specific blob of events in my graphs that I can't seem to understand, and then building a hypothesis of what it could be, and then testing with other data or with some specific calibration of some specific simulation. And yes, it's that. Yay, we got one out. Next.
So it's troubleshooting the detectors was the most exciting for you.
Yes. So the way we take data. So our data is a bunch of things. Like I said, we just throw a net and we try to get things out. So to get another science north or dynamic curve analogy, it's like looking for gold at a dynamic curve. So, but instead of having just your small scoop of sand that you try to get out, and then figuring out what's left inside, and if there is something shiny that's staying at the bottom, well, you have few metric ton of sand, and you have probably some mechanical device that brings part of it out that it's not going to be gold. So it's, for instance, you put that into water, and everything that somehow dissipates in the water cannot be gold, obviously. And then at the end, you have all that. So you have your events that or your gold that is looking like something you want. But of course, people like Dynamic Earth are not that nice with you. They are also going to be putting some full gold inside. So that's also some shiny yellow stuff. And they are putting some of those purple, like I can never remember the name, stones that are also looking shiny in the water. And then, and so you have to somehow figure out how to select each of those specks one after the second. And hopefully at the end, you have something that is actually looking like what you are looking for.
And right now you've got a whole lot of fool's gold and little purple specks of amethyst, and you're really filtering through all that. And there's just that little bit of gold that keeps you going.
I hope they didn't forget to put it. that will be mean.
Oh, no. We definitely do put gold in there. I can assure you from an inside perspective, it's there.
Well, if you get at the end of the day, I don't know how much gold there is left.
less and less by the end of the day. So that's your pro tip, I guess. If you learn nothing else, it's come early to Dynamic Earth to get your gold. Unfortunately, I think that's just about all the time we've got. Renata's poking me at the chat to wrap this up. So I want to thank you again, Pierre, for joining us and for having an excellent little chat here on our Bluecoat Talks. And I want to thank everyone in our audience for showing up on this beautiful afternoon when you could be outside social distancing. Thank you for joining us, and I hope you all learned something. I know I did.
And thank you for having me, and have a very good day.
You're very welcome. Have a good day, sir.